Several technological devices of the 20th and 21st century have been made possible by semiconductor devices. Consider, for example, LED lights, which are up to 75% more efficient than incandescent light bulbs. Or think about the smartphone you might be using to watch this video, essentially a powerful computer that fits in your pocket. The fascinating physics that enables these technologies often takes place at interfaces. In this video, we briefly explore the operation of three fundamental types of interfaces at a high level: p-n junctions, metal-semiconductor junctions, and heterostructures. An interface is defined as the boundary of two surfaces in contact. Thus, we begin our discussion here. You may have noticed that crystals like quartz or emerald are cut into distinct shapes. This exposes several distinct surface terminations. Within a crystal, atoms are arranged in a regular pattern termed the bulk or substrate. When cleaved along a specific direction, a surface is exposed. To minimize energy, the surface atoms will often rearrange such that it is no longer in registry with the bulk, in a process known as surface reconstruction. Experimentally, reconstructed surfaces are often characterized using spectroscopy, such as lead spectroscopy or STM. Work function is important to an understanding device physics. It is governed by the following equation, where phi vacuum is the energy of an electron taken infinitely far away from the surface, and EF is the work required to add one electron to the material, the Fermi level. Put simply, the work function quantifies the energy needed to remove an electron from the surface. Importantly, the orientation of the crystal surface affects the work function values. In essence, this is because different surface terminations expose distinct chemical environments to vacuum, which in turn affects the energy needed for electron removal. The concept of work function actually lends itself nicely to the principle by which incandescent light bulbs operate. First, a current supplies heat to an electric filament. This provides the energy needed to dissociate electrons. The phenomenon, known as thermionic emission, is governed by the Richardson-Dushman equation, which describes how the current density of electrons emitted, Je, is related to the material's temperature, tau, and work function, phi. As we might expect, the equation predicts that hotter, low work function filaments shine brighter. The simplest device we can discuss is the p-n junction. Imagine you have a thin slice of silicon, called a wafer. The pristine crystalline silicon lattice is not very interesting on its own, so impurities are often introduced by bombarding one side of the crystal with boron ions and the other side with phosphorus ions. Because boron has one less valence electron than silicon, this side will become electron deficient, which we call p-type. Because phosphorus has one more electron than silicon, the other side will end up electron abundant, which we call n-type. At the interface, electrons from the n region will diffuse to the p region, resulting in hole accumulation at the boundary of the n region and electron accumulation in the p region, an area known as the depletion or space charge region. This diffusion process is denoted by the formation of an electric field, J&G, or the generation current, pointing from the p to n side. As a result of this current, some electrons will drift from the p to n side, which we highlight as JNR, or recombination current. Let's look at the effect of an external electric field on the p-n junction. At reverse bias, negative voltage is applied to the p region, and positive voltage is applied to the n region. This causes electrons to accumulate on the p side and holes to accumulate on the n side, increasing the potential difference, which makes it difficult for electrons to drift back from p to n and reduces J and R. At forward bias, the potential difference decreases, which increases J and R. We can derive a simple expression for the total current in the p-n junction through some simple algebra, knowing that J and R changes by a Boltzmann factor, which is a result that comes from statistical mechanics, and that at zero bias, J and R and J and G are equal to 0. By summing both J and R and J and G, we find that the total current can be simplified as follows. We can extract some physical insight from this result by observing its limits. Particularly, we find that as voltage goes to negative infinity, current goes to 0, whereas when voltage goes to positive infinity, current goes to infinity. Now it becomes clear why the junction acts as a rectifier. it only allows current to flow under positive bias, acting almost like a check valve. Another application of p-n junctions is that they form the foundation of solar cells. If a photon of sufficient energy strikes the junction and is absorbed in the depletion region, an electron-hole pair forms. Electrons are then driven toward the cathode and holes toward an anode via a built-in electric field which generates a photocurrent. Compelling physics arise at the interfaces of semiconductors and metals. Let's begin by assuming the Fermi level of the semiconductor is higher than that of the metal. In this case, electrons flow from the semiconductor conduction band to the metal. Similar to the p-n junction, this charge transfer creates a positively charged depletion region within the semiconductor, and a negatively charged depletion region within the metal. The generated potential difference results in band bending and the formation of the Schottky barrier, phi Bn, as shown. The Schottky barrier height represents the energy barrier an electron must overcome to flow from the metal to the semiconductor. Given that there is a perfect contact between the metal and the semiconductor, we can crudely approximate the Schottky barrier using the Schottky-Mott limit, where phi m is the metal work function and chi s is the semiconductor electron affinity, or the energy an electron needs to escape from the conduction band minimum to the vacuum E0. However, in reality, there are often states that lie within the semiconductor band gap, arising from either intrinsic semiconductor surface states, think about surface reconstruction, or from direct bonding with the metal, which are known as metal-induced gap states. If there are enough of these states, an energy level E neutral separates donor-like and acceptor-like surface states, effectively pinning the semiconductor's Fermi level. This causes the Schottky barrier height to be independent from the Fermi level, apparent in the Bardeen limit equation. In practice, Schottky barrier lies somewhere in the middle of these two limits, as follows, where S is somewhere in between 0 and 1. Due to the Schottky barrier, metal semiconductor junctions can also function as rectifiers, commonly used in Schottky diodes. Additionally, because the Schottky barrier forms as a result of electron transport, it has a low forward voltage drop where electrons do not have to fight against drift currents, benefiting from ultra-fast switching between on and off states. This makes them suitable for use in high-frequency devices and efficient rectifiers. We can actually tune the Schottky barrier height to optimize device performance. From our previous discussion, we might theorize that manipulating the metal and semiconductor used, as well as the interfacial contact, might be a good place to start. More recently, researchers have used electric field control and strain engineering to tune the barrier. When two or more semiconductors are interfaced with each other, they form heterojunctions. These can be thought of as single crystals with different atomic sites at the interface. Semiconductors have distinct band edges presenting in one of three specific band alignments as depicted. To model charge transfer across band alignments, we note that electrons sink and holes float according to their bands to lower energy. This property allows different heterojunction band alignments to be useful in different contexts. For example, the staggered band alignment is preferred in photocatalysis, as electrons and holes will accumulate on different materials. This reduces the likelihood that an electron will meet a hole and they'll annihilate each other, which decreases photocatalytic efficiency, a process known as recombination. Despite its name, the broken gap band alignment has proven to be quite useful for a special class of devices named tunnel field effect transistors, or TFETs. This is because the broken gap alignment facilitates electrons to flow from the conduction and valence bands of one material into the conduction band of another, with the latter transfer enabled by a phenomenon known as band-to-band tunneling. This tunneling allows for TFETs to function as fast switching in low-power electronics. Like the Schottky barrier and metal semiconductor junctions, band offsets and heterojunctions can be manipulated to optimize device performance via similar methods such as interfacial strain, electric fields, and defects. Before we wrap up, I want to thank everyone for the support on my previous video. I also apologize for the delay between uploads. Moving forward, I'm aiming to post more regularly, about once every couple of weeks. This summer I've been diving into a few AI side projects, and I'm excited to share them with you soon. These include an EKG heartbeat classifier, a quantum mechanical property predictor, and an end-to-end speech recognition application. I'll be releasing videos on each of these in the coming weeks. If there's a specific topic or project you'd like to see covered, feel free to drop a comment below. I really enjoyed connecting with the community on the last video. As always, if you found this content interesting, don't forget to like the video, subscribe, and turn on post notifications so you don't miss what's next. Thanks again, and see you in the next one.